So in this video I'm going to be talking about half-life and how it relates to radioactive emissions. So the definition of half-life is how long it takes for half a sample to undergo radioactive decay. So how long does it take any of the radioactive materials we've already looked at, how long does it take for them to undergo one of these three emission types, alpha, beta or gamma, or a combination of the three. So how long does it take for you to have half the sample left over? So a good demonstration of half-life is if we take a piece of paper. Nope, need that one. So we take a piece of paper and you rip it in half. And you may have done this kind of thing in algebra when you talked about fractions or even pre-algebra, but you'll never reduce the piece of paper to absolutely zero, because there's always going to be half left of whatever smallest piece I can rip this to. So I keep going, and yes, these are all perfectly measured to exactly 1/2, but it's going to get smaller and smaller, but I'm never going to really end up with absolutely zero, because there's always going to be some left. My fingers are too big to rip it, but I don't want to get the tweezers out to labour this point, but basically I'm never going to get to zero. There's always going to be some left. Same idea with radioactive materials. It'll go through this decay, or one of these three emission types, or combination, and then it's never going to be absolutely zero. There's always going to be some left. Whether we can measure it, whether we can detect it is a different story. The technology exists for fairly sensitive levels of radioactivity, but it'll never be zero. So the idea of half-life, a good example is carbon dating, which you've probably heard a lot of. It's on the news quite regularly. But there's some misconceptions that happen on the news. It's presented for non-scientists, right? So they usually take some massive liberties with the truth, and especially Fox News. Anyway, so we'll talk about radiocarbon dating, which is using a radioactive isotope of carbon. So remember that on the periodic table there's a certain group of elements all over atomic number 83 that are radioactive, but for all the other elements there could be a radioactive isotope. There are definitely isotopes for all those other elements, but not all of them are radioactive. For carbon, carbon's got a couple of stable isotopes, 12 and 13, and then carbon-14 is the radioactive isotope. So how does this isotope, how is it created? Well, and how do we actually use carbon dating, and how does it eventually relate to half-life, and how does it eventually relate to nuclear chemistry? So that's the big goal of this. Oops. So the idea of how carbon-14 is, there's always a certain level in the atmosphere, there's always a certain level on Earth, not on any other planet, just our planet, not the moon, just our planet. So the idea of going to the moon and trying to measure the half-life of a moon rock isn't going to work because there's no carbon-14, right? So, but we can use carbon-14 on carbon-14 dating on this planet only. So how they're created is cosmic rays from our atmosphere, from our sun, produces a neutron. And in our atmosphere we've got a load of nitrogen. The air that we breathe is about 3/4 nitrogen gas. So there's loads of this, nitrogen-14, which is the regular isotope. It's the most abundant, most stable isotope of nitrogen. So a neutron comes along and collides with this atom, and what's produced is carbon-14. So if you look at, we're looking at the balancing of this. 14 plus 1, a proton is produced. So as well as an atom of carbon-14, which has the same mass number but one less proton, the mass of a proton combined with the mass of this atom equals this. So if you just look at the numbers, 14 plus 1 is 15, same here. 6 plus 1 is the same as 7 plus 0. We're all good. So, so that's where the carbon-14 comes from in our atmosphere. So how does it end up in animals and plants and organic material that we use carbon dating to actually date? Not dating that way, but just dating how old they are. So the carbon-14 that is in our bodies right now and is in all organic material, and the definition of organic material is anything that contains carbon. So that includes most or every plant every human being, every animal, and any living thing contains carbon. So, so the carbon-14 actually ends up in carbon dioxide, which is the gas that plants breathe, and we eat plants or we eat other animals that have eaten plants. So there will always be a certain amount of carbon-14 in animals and plants. It's a really, really tiny amount, and it's actually the ratio of carbon-14 to carbon-12. Carbon-12 is the most abundant isotope, stable isotope, but the ratio is one atom of this radioactive isotope to a billion of the stable isotope. So 1 to a billion is the ratio. So a really tiny fraction of the carbon-14 is inside us, but it's definitely there. And actually, just a side note, carbon-14 undergoes beta emission to produce nitrogen back again. So when we die, or when plants die or other animals die, we stop taking in or maintaining that level of radioactive carbon, this much. So we're not breathing in or not consuming carbon in any way. So we stop eating plants when we die, and animals obviously. So we're not taking in this fresh supply of radioactive carbon. So the level, which is this roughly, this gradually drops, and it drops by a certain amount, which is actually the half-life of carbon. All radioactive isotopes and elements have a half-life, and it's how long does it take for half of the sample to undergo radioactive decay, to do something like this, or one of these. In the case of carbon, though, it undergoes beta emission to produce the nitrogen back into the atmosphere very slowly, but it does happen. And this electron will be accepted by another atom or molecule that won't exist on its own for long. So that's how we end up with carbon-14 in our atmosphere, and then in our bodies, and then in plants and in animals which we consume, and then that level of, while we stay alive, that level of radioactive carbon, so this ratio, stays the same. As soon as we die, it stops, and then it starts to do this, starts to decay. So the half-life of carbon we'll talk about, of this radioactive carbon we'll talk about in just a second, but that's the basic overall picture of how carbon dating can only date things that have been alive. So nothing on the moon has been alive. So anything that's consumed carbon dioxide in the case of plants, or animals that have consumed plants or other animals. So that's where it all comes from. So within us right now is this level of radioactive carbon. As soon as we die, it starts to decay. Okay, so that's just a basic overview of carbon dating. Oh, one last thing to say. So I think that varying sources, depending on the level of Geiger counters that you use or other measurements to detect radioactive material, carbon dating is really only good for about 50,000 years, and even in some cases 100,000 years. It's just that there isn't enough to detect because the ratio is so tiny. So for every this many nanograms, there's only 1 nanogram, which is really, really tiny, of the carbon that's radioactive. So a really tiny amount. So it's really difficult to detect, and that's why it's not accurate beyond a certain time frame. And that's usually around like 50,000 years. Most sources say 50,000 years. Okay, so I'm going to erase this. So if you hear on the news that someone is trying to date stainless steel with carbon dating, shout at the television that they are liars and it's not true, because you know better, because something has had to have been alive to use carbon dating. Alright, so carbon-14 has a half-life. Well, I'm going to go out on a limb and say that many years, 5,730 years. Many sources say it's plus or minus 30 years, right? So you might see a slightly different number, but we'll just use 1 just for the sake of convenience, and that's the half-life. So that doesn't mean that, say if this was our sample of carbon, what this does not mean is that after that many years, exactly one half just goes away. It's not that straightforward. It's much more random. And in fact, half-life is a probability. So it's how probable is it that half the atoms will undergo radioactive decay. So imagine that this is our box sample, and these are all the atoms of radioactive carbon. After 5,730 years, you've got half the amount. So if we started with, say, 100 grams of carbon-14, after this many years we'd have 50, which is half. So after another half-life, and a half-life is this many years, we'd have exactly half that number, which is that many. It isn't like this idea of just ripping a piece of paper in half and just half that sample goes away. It's much more random. So any one of these atoms could be undergoing the decay, but after this many years there are half left. Another half-life, half again. So that's the idea of the half-life. Just quickly erase that. So while I'm erasing, you could be checking Facebook. I'm joking, of course. So if we plotted a graph, so let's say that this was 100% of our sample. So that would be half-lives on the x, and then this is 100% of the sample. I'm actually going to change that slightly. I'm going to start using the official notation for half-life, which is a T with a subscript of 1/2. So if this is 1, 2, 3. So you can plot this on a graph, and we'll actually do this in class as an activity, just so you get the idea. Obviously much easier when the graph's on graph paper, but 50%, let's say it's exactly there. So after 5,730 years, you've 50% of the sample undergoes radioactive decay, changes from carbon-14 into nitrogen. Then after another half-life, that amount decays another 50%. So this would be 50%, this would be 25%, and then another half-life goes by, so that would be half of 25, 12.5. So we started off with 100, half of that is 50, half of 50 is 25, half of 25 is that, and we keep going as we're adding half-lives until technology lets us down. So we can't, it's really difficult unless we really zoom in on this graph to look at 7 half-lives because of the scale of this graph, but the graph actually has a curve. So the way that it decays is exponential decay. So it's not decaying in a linear fashion, a straight line. It's decreasing in a decreasing rate. So it's curved this way. If this freaks you out, that's okay. That's as much, for this video, that's the level of detail of math that you will need to know. Just, it's exponential, right? So it's not a straight line on the graph. It's a curve, so it's not that. So the idea of half-life is that every half-life you've got 50% of the sample left. That 50% is random. It could be, you can't predict which particular atom it's going to be. You just know that it's half of them. So every half-life you lose 50%. And on a graph it will look like this curve idea. So that's the idea of half-life. Let me just show you an example type problem. Alright, so you know the half-life of carbon, and actually you'll never have to memorize it. You'll always get that information. You'll always have a reference material or reference materials to access half-lives. It's not the kind of thing you need to memorize. You'll always be given it. Okay, so to do some calculations, the level of calculations for this video is that if you know the half-life of carbon, I would probably ask you how much after how much of C14 would be left if we start with, I should have written this out at the beginning, start with 5. So we start off with 5 grams of carbon-14, question mark. How much will be left after 3 half-lives? So the way that you answer this problem is different ways to do it. I mean, you could just say, well, 1 half-life is 57 years. So then, if we start with 5 grams, after that many years we get 2.5 grams, so it's 50% or half, and then another half-life would be 1.25. So that's so far that's 2 half-lives. 1 more half-life, so that's a total of 3. How much of carbon-14 would be left? Well, it's half of this, so that's OD&D 6. 0.625 grams. So that'd be our answer. So the first level of problems of dealing with half-life is this. And so really what I'd expect you to be able to do would be to calculate how much of a sample would be left if you know the half-life. And that's it. That's all you need to know, or the very, very minimum. So half-life, again, is how long it takes for a sample to undergo radioactive decay. It isn't just 50% exactly, it's just cut off and decayed. It's much more random, and you can't predict which atom is undergo radioactive decay any time. You just know that 50% or exactly 1/2 will. 3 different types of decay or emissions could happen. Depends on the atom, depends on its size, number of neutrons and protons, to predict which one it undergoes. Carbon-14 dating we will learn more about, and why it's very useful in class. We talked about where it came from. It comes from the atmosphere, and then the same level of carbon-14 is in us all. When we die, we stop maintaining that amount, so then it starts to undergo beta decay. And it's got a half-life. So, for example, if we have 5 grams in our bodies of carbon-14, after 3 half-lives, which is 16,000 years or a little bit more, there'd be this much left. And gradually we'll never get to 0. And the last thing to say is on a graph it looks like a decay curve. If you're in Algebra 2 or higher, then you've learned about that. But exponential decay, so it's not decreasing in a linear fashion, it's a curve. And that's it.